episode of our Prague seminar for mathematical physics. And I'm really glad to see you here, despite not sending a reminder message and some technical problems from the very beginning. And what's even nicer, we have here our kind speaker for today, David Osten, a researcher from University Wrocław in Poland. And I guess David bring among us a very compelling topic, current algebra and generalized Cartan geometry. So I think we have enjoyable time before us. So if no objections, we can kick out today's talk.
Okay.
So please, David.
Yeah. Thank you very much. Thank you for the an invitation. So yeah, I'm very glad to talk to you about our current work on basically looking at the generalization of Cartan geometry, basically motivated from the current algebra of the classical string. So this is based on a recent paper, as probably noticed, together with Falk and Ondra. Falk is, I guess, also in the audience. So this is work that builds on several existing other works. So probably the most crucial one is this almost 10 years old approach to the current algebra by Polacek and Siegel and to the construction of curvature. And this has been roughly 2 years ago re-examined by this group. Yeah, and we also connected, we basically do also generalization of this work by Sylvain Lacroix on how to phrase string dynamics in a covariant way under some gauge symmetry. So, I mean, it will all come into some context. So what I will talk about in this talk, so after some very brief introduction to generalized geometry, to just get the all the definitions and maybe also the problem, right? I will, as a motivating example, look how Cartan geometry is actually realized on the point particle phase space, which then directly leads to a generalization to the 2D sigma models, and also very natural generalization of Cartan geometry from the point of view of generalized geometry. And then, we'll phrase this in the metric formalism and look how this looks for a metric compatible connection. And yeah, in the end, I will comment, if there's time, a bit on covariant string dynamics. Okay. Then let's go to some basics of generalized geometry. So what's generalized geometry? Basically, it is the geometry of the generalized tangent bundle. So instead of looking at just vectors, we look at the bundle of vectors and one forms. So what I typically will write as a generalized vector will have will look like that. So it has a vector component and a one form component. And now the question is, we want to do maybe Riemannian geometry on there. So we want to define metrics, and actually there's two kinds of metrics here. So we have the canonical ODD metric. So this is basically the canonical pairing of vectors and one forms, and the actual kind of geometric metric that tells us something about a concrete manifold is what typically called generalized metric. So this is some object with such indices in the in this generalized tangent bundle, which is some element of this coset. So this, hopefully all know, this will encode metric and B field, or in general, this will encode our geometric information, whereas this will raise and lower indices. Okay, and then we also want to have diffeomorphisms and so on, and generalization. So these are the algebra is given by generalized Lie bracket. So this is also called Dorfman bracket, or in general, this is the algebra of generalized diffeomorphisms. So just give that. So if we have two of such generalized vectors, V and W, we find an object like that, which is obviously an ODD vector, and so this is also what we would consider the Dorfman bracket. So, and I mainly introduced this section to introduce notation. So I mean, he introduced this derivatives. So we are here working on some manifold M, so with coordinates x m. So this object just looks like that, but we could generalize this to some generalized coordinates, but then we need to impose a section condition, so that any combination where the two derivatives act on something, this is 0. Okay, so it's just to give basic definitions. Now what we want to do, so what is the aim of this program, is to understand where, what is curvature, what is torsion, and in general, the first step for this would be that we want to understand what a connection is. So I mean, I call it generalized connection. It's just a connection on this thing. So so the aim is, again, to define some object as an ordinary geometry, where this is, again, a generalized tensor. So in the sense that it's something that transforms in the correct way under this Lie differential, or under these diffeomorphisms. So and for that we introduce these Christoffel symbols in such a way that this is a tensor. Okay. The thing we actually will be concerned with here is how to define curvature and torsion. So so we have this connection, and we can just define curvature and torsion in a naive way. So for example, for the for the curvature, this would be the naive definition, basically just substituting ordinary tangent space indices by this generalized tangent space indices. But it turns out, so this is well known, that this is not a tensor under generalized diffeomorphisms. And for this reason, one has to define a different object as curvature. So this is probably done by Siegel and Bohm and Zwiebach. So we look at this combination. This is a generalized tensor, and so in the same way, one can check quite easily that the naive definition of the torsion, not a tensor, instead so this object is, so we need to modify our definitions of generalized curvature and of definition of curvature and torsion in order to be compatible with these generalized diffeomorphisms. And yeah, in principle, this is the question that Polacek and Siegel wanted to answer is, is this natural definitions? Are there other definitions? What is the metric interpretation of these changed definitions? And so this is basically where, why we thought about this generalized Cartan geometry, is that this will be a very nice explanation on how this definition comes to pass. Okay, and just because it will be relevant in the end, so this is maybe the one problem was is to understand actual definition or the geometric interpretation. The other question is there or how can one understand what the generalized Levi-Civita connection is? So if we impose compatibility of this covariant derivative with eta, the generalized metric, and even if we introduce some compatibility with the dilaton and like set portion to 0, this still means gamma will be not, so the connection will be not uniquely determined. There will be undetermined components. And so this is a problem we will not answer here. Maybe this approach will be useful to attack it from different perspective, but and later I will discuss a bit what these curvature components might mean for these fixed components. For this, let me introduce some basic definitions. So typically one introduces that projectors so that, for example, we define like that, or that. So we decompose our generalized tangent indices into overbarred and underbarred indices with help of these projectors. And turns out that in this decomposition, this connection will decompose into several components. So this one, so it will be decomposed in one component which will be uniquely determined by these properties, and it will decompose into something that is not determined, and these are these two components, and these will be traceless if we contract one of the first and one of the two other ones. So this is so this is the undetermined part. It is a very concrete part of the connection. But yeah, so this is not what we will solve, but it is something that we will use later to analyze how physical one of the additional components of our connection and curvature will be. Yeah, and just as one thing, so for example, things that you can derive from this computability, which will actually be used just as an example, would be that the naive curvature, for example, as this property, for example. So this is something which will be used in the computations. Of course, I will not change that show the computations in detail. Okay, so this just as the necessary basics. Okay, so now let's go to what's the geometric interpretation of these curvatures. And for this, let's start with a point particle. So yeah, and maybe let's give the basic ideas of Cartan geometry. So yeah, I mean, I'm not a mathematician, so please be patient with me that it will be a very sketchy definition. So what's my idea of Cartan geometry is basically that you look at the tangent space over some point, and you model it that it's not a vector space, but you try to model it that it is basically a quotient of Lie algebras, where I will call G as the model algebra and H as the gauge algebra. And yeah, another way to look at it would be that you try to model the manifold itself by such a coset space. So this is often called a model space. And so yeah, the prototypical example, which will also in generalized case be a good example where it is even a bit more non-trivial, is that, for example, G would be Euclidean algebra or Poincaré, and H would be Lorentz group, or what representations, or the Lorentz group. Okay, so then this quotient would be just R to the N, and this H would define some kind of action of rotations on this. So this would be just basically ordinary geometry phrased in this way, but you can generalize this to other algebras, for example, the ADS isometry algebra. Okay, but now we want to define connections and curvatures. So this is our motivation. So the underlying object there is actually a principal H bundle, where H is the Lie group to this H, and so the Cartan connection is, so I hope with a small theta, is basically this identification, but extended to this principal bundle. So the Cartan connection in general is an isomorphism between this principal H bundle and this Lie algebra, and for each point of this bundle. And then this has to fulfill basically two properties. Basically, if we restrict it to the H part, it would be again also an isomorphism. So we just identify basically left invariant fields, for example, or right invariant fields in this thing with elements in H. So would be some map H, and yeah, a bit more non-trivial is so-called equivariance, which basically tells you how components or how this object transforms under H, the action of H. So this is typically given in this form, but we will use it in different form. So the way how it will appear on the phase space is, of course, in some kinds of coordinates, or it's at least for me easiest to understand. So how I will look at it, I will look at that this are indices on TP, and these are indices of G. And then turns out you can always fix this connection to this form. This would be an A. So where I use menu and so on as indices of H, and A, B, and so on as indices of coordinates. So so I use and M and N would be the indices for G without H. So these curled indices, they decompose into mu and M, and the same for alpha and A. Okay, so this is just one way to write, and this is also not the unique way to write. So here, for example, we just fixed this part, which would be the restriction to H to be the one. But the important thing, the geometric part, is that you see we have as a freedom remaining after this assumption is that you have something which will be can interpret as a spin connection here, and you will have something which will be a frame here. Okay, so this is how we define a connection. And as I said, we are mostly interested to define curvatures, and so the Cartan curvature, you can simply derive from here, where this is the Lie bracket of G, and we use that basically these indices. These indices M, Lie algebra indices, and these are basically form indices. So this is how they are understood. And so the non-trivial components of this object will look like that. So is where we have here in this form index the target space indices. So this would be a 2 form, and here we decompose this again as the H valued part and the G over H valued part. And turns out that these are just indeed the definitions of curvature and torsion in the terms of spin connection and frame. So this sense, this Cartan geometry very nicely encodes torsion and curvature inside one object, which is defined in terms of this connection and this very natural definition. Okay, and maybe just one last comment on that. So here we have this expression of curvature, and just to translate it to like an ordinary way to write down Riemann curvature in this index form, I would write it like that, where this is these are structure constants of the action of Lie algebra H, which has generators mu in my language here, acting on vectors, tangent vectors. So this is why we have here. So this is basically just a representation of H acting on vectors. Okay, so I guess this is also fairly standard, but what's interesting that it's not standard, that this is very canonically realized on the point particle phase space. So again, let's look on manifold M with coordinates x, xm. Then we have canonical momentum is kind of like that. And in particular, we have just the momentum which commutes. And now we assume that we have some H gauge symmetry realized on the phase space. So we just assume that there are some phase space functions S, which form out like that. So these are structure constants of H. And so this is what I already kind of mentioned. There's some kind of action of H on the tangent bundle, and this is realized on the phase space as having some non-trivial commutation places between S and P, which looks like that. And yeah, so now we have basically these relations. So this is one basis of our phase space, but turns out there's a very nice other basis of the phase space. So this is the basis of phase space that we have together with these functions that generate the gauge symmetry. So in the momenta and this, but yeah, we can look at the different bases, and for that actually we will exactly use the Cartan connection, or in this expression that I showed, which basically look like that. And then it turns out that if you compute the Poisson algebra of these new functions, you will get exactly, so this is now a big theta. We'll get as coefficients here exactly the Cartan curvature out. So basically this Poisson brackets together with that we use, of course, that these depend on x, and we also have to, which I didn't show, basically assume things for these brackets. So this is basically, this will be determined by this equivariance principle, so that there's some transformation behavior of spin connection and frame under this H gauge symmetry. And if we assume this in the right way, we will get out that yeah, on the phase space, this is yeah, it's a way to compute the Cartan curvature. Okay, and just as a side comment, I mean, I will comment on it more in the string case. So why is this a nice basis? So it's a nice. Yes, please.
So this omega and E, they are viewed as functions of x only, right?
Yes.
And this S are some function of x and p, and we don't know anything about linearity or something, or how, what do we know about? Is it homogeneous or something, or what are this S?
This, I mean, this would be, I guess, in the easiest case, you could, for example, see them as Lorentz generators, and then I guess you could, for example, think about them as, so in the case it's Lorentz, it would be something like that, x, or maybe n.
But how is it? I mean, the Poisson bracket kills one momentum, so doesn't it need to be linear up to things which vanish? At most linear or something. If it's quadratic and quadratic, we get a third order term, right? Which is not in S.
Yes, maybe.
Okay.
Yeah, I haven't thought about it this way. Yeah, I mean the way how you could, the easiest way would be something like that. So this this would be the action of Lorentz. But I mean it. So here this you would have. I mean, if you take different coordinates x, there could be something more complicated here, and it's so I assume that these are a constant, but yeah, maybe if you have to assume that these are not constant, then you can assume something else. But yeah, it's a
I think as written, it can be at most linear in P.
Okay. Thank you. Yes, I think I guess you're right. Yes. Okay, and yeah, the question is, why is this a good an interesting basis? So basically the Hamiltonian, which would, I guess, normally be proportional to something like this, you can just also write it in a very canonical way in terms of these currents. So basically, because of the frame here, you will diagonalize this metric. And of course, you have now a bigger coordinates, but of course, because you assume that this is symmetry, you will want that these S mu are 0, and this will say that these two things are equivalent. So this is just a very convenient basis of the phase space as well. So okay, then are there other questions so far? Or I continue with the generalization. Okay, if not, then we continue. So yeah, I was thinking how to motivate this thing. I mean, it was derived from the string phase space by Polacek and Siegel in some way. It was not interpreted in terms of generalized Cartan geometry, but was derived that way. But I guess it's still more straightforward just to define what I mean by generalized Cartan geometry and then look how it's realized on the phase space. So again, I look on some H principal bundle. So this stays the same. What as input you basically want to have is some action of some symmetry group H. But now this will become clear why it's necessary. So far we had that we want to model the tangent bundle by this quotient of Lie algebras, and we had G as the Lie algebra, but here I want to have the model algebra, which I call D now, will be actually be a 2D plus n dimensional, and yeah, we called it quasi-Lie by algebra. So D would be dimension of M, n would be dimension of H. So normally the model algebra would be a D plus n dimensional Lie algebra. Now we say in the generalized case we have a 2D plus n dimensional quasi-Lie by algebra. And so what do we mean by this term? So typically a Lie by algebra is one where you have G and the dual G bar. So we have some kind of symmetric pairing, which again I call eta. But typically, so we look at an object like that between two algebras. Typically, a Lie by algebra would impose that both G and G bar is the subalgebra. This is what we don't need to impose here. The only thing that we need to impose in addition is that this algebra H is contained in here. So it contains the subalgebra, and it is an isotropic one. Also, we are also not quite clear how much this is necessary. Okay, and maybe it becomes clearer why we want to have exactly this structure is because the natural generalization of the Cartan connection would be now not to have identify just the tangent bundle of M with something, but we want to identify the generalized tangent bundle with something. And so what is generalized Cartan connection for us is a map between the generalized tangent bundle of this H principal bundle to this model Lie by algebra, quasi Lie by algebra. So, and this again has to be in isomorphism as a vector space. And in addition, now, because we have this additional structure of the symmetric pairing, we also want that it preserves this eta. So here we have canonical metric eta, and here we have this pairing. So this should preserve that. And again, if you, we will require equivariance, and also again that we want to identify the restriction of on TH. So this will restrict the form, and it turns out that we have a general form which looks as follows. Okay, so this is the form which again follows from fixing basically this comes from here. So let me again show what these indices are. So these M are indices on D, and this D composes into H. This is a subalgebra. It will be composed into something else, and it will decompose into something which is, because we have the symmetric pairing, will compose into some within a dual vector space. So this would be why these indices decompose like M and like that. And here, so this would be a 2D dimensional remainder of the Lie algebra. So this would be, goes over 2D. And in the same way, these A are indices on T plus T star, where the alpha index, for example, would correspond to TH. The alpha up would correspond to T star H, and the A indices would correspond to the generalized tangent bundle of M. Okay, so this is the indices, and now if we look what is inside here, so if we just look at This part, this looks basically the same as the ordinary Cartan geometry. So this is what we call generalized spin connection. This is what we call generalized frame. Then we have a part here which is fixed by basically the fact that this has to be preserving eta, but we have some additional freedom. This is this additional field rho, which was introduced by Polacek and Siegel. So we call it Polacek Siegel field. Okay, so this is our definition of generalized Cartan connection, which is basically arises from the very natural generalization of that we would now consider the generalized tangent bundle of the spin-field H bundle and not just the tangent bundle. Okay, and with that, we can also define generalized curvature. And now it's a bit tricky to define, because before we defined it as like d theta something, but on this generalized tangent bundle one would need to work a bit harder to define just what the d is. Of course, probably you can do that, but the way that we defined it is we used a twisted Dorfman bracket on yeah. So how does this look? So now we look at two things. So this twisting I denote by this D here, which suggests that it's probably related to this model by algebra. So we have the standard terms. But we have a twisting by the, so this is the structure constants of D. And so for this, yeah, here I've used this big D, suggesting that it's not just derivative. So, so this is also some kind of twisted derivative, so which decomposes into something like that. So basically now we are on a very big tangent space, and this derivative suggests that we could do derivatives to all of the coordinates. So this would be derivatives with respect to the coordinates on H. And this would be the duals. So this is what we set to 0 normally. This is yeah, basically how H would act on a vector. So we don't assume that there's dependence on the coordinate itself, but we assume that it can rotate. And this would be some kind of derivative, and this in fact could also be non-commutative. So in order for this twisted bracket to make sense, we would need to assume that we have an algebra like that, and it turns out if you take a particular cases of D, which would so for particular D, you can find ones where this one is this commutator between these derivatives is 0. So this would be correspond to a flat case. So this is what we would call, generalized Poincare type. But in general, this whole procedure would work for arbitrary ones, but then you always need to assume that we have some kind of non-holonomic frame, basically. Okay, but if you have this bracket, then it's easy to write down a generalization of this thing. So the generalized Cartan curvature looks as follows. So we understand the connection. So this object as a vector in D. So don't write down this index. And we just compute this twisted Dorfman bracket. And this is our definition of the generalized Cartan curvature. Okay, and so now these A, again, they have, just to make sure, they have this decomposition. So this should be calligraphic A and B, and this would be normal ones. And in particular, now this, of course, has many different components. So, for example, let's maybe write down this algebra index also. So this, for example, decomposes into object like that, decomposes into an object that and object like that. And so, I mean, I will comment soon on what this interpretation is. So so this would be portion. Here we will see what it corresponds to, and this in fact will be not independent, but yes. So this is basically if you decompose this into these different objects, and they will correspond to like curvature or torsion-like objects. And for example, with object like that, you will do the same thing as in the, so this would looks like Riemann tensor-like term. It will turn out it will be not only that. So so we could have object like that. Where again, so this is structure constants for the action of H on now T plus T star of M. So you can define objects with just M index structure like that. Okay. Yeah, so I think in view of time, I will jump how this is realized on the string phase space, and we'll discuss what actually these objects mean in terms of the or typical objects of curvature in generalized geometry and double field theory. So
may I ask something or make
yes,
a
please.
remark? I don't know.
Yes.
So did you think about more general Courant algebraics instead of the standard one? Because this looks very much like this, right? So like if you have G plus G star, it can be also Courant algebroid, just over a point. And T plus T star is just an exact one.
Yeah.
But if you take a more general one, you have a lot like both of these players in the game.
I mean, no, we didn't think about it yet. I mean, yeah, maybe it's a good point because in general, it's yeah, in some sense, we have a weird structure here where maybe it's good to think about in terms of current algebroids, because I mean, in the end, we are interested in objects on T plus T star on M. And so we are kind of reducing, so we don't assume that any physical functions will have coordinate dependence on H. So in some sense, we have a different structure than a normal current algebroid. So yeah, maybe it's a good thing to think about what other structures one.
But this H also looks like a small Dirac structure in this G plus G star. So
yeah,
I think it may be a good perspective. Okay.
Okay. Yeah. Thank you. Yeah, but I mean, in such, I mean, if it's we look from the from this motivation, which I now will not discuss, from the string phase space. So on the string phase space, we have a natural. So this arises naturally. This current algebroid structure. So from there, it's maybe not so easy to see what one could get different, but yeah. Okay, so let me continue to maybe shed some light into what these objects mean. And I also, I mean, now I haven't given concrete expressions into what, basically what I haven't given yet is how this big generalized Cartan curvature, how this looks in terms of the actual interesting fields. So generalized spin connections, generalized frame, and also this Podolacek Siegel field. So this here. So now, yeah. So far we have basically given everything in terms of spin connection and frame. But just to make the expressions to be understandable easier, you can also write them down in the metric formalism. And then actually the components, the non-trivial components, these are the ones that I have written down here. So there's other components, but they are basically all determined by the model algebra, by the choice of model algebra, so they don't contain geometric information. So yeah, so the only interesting components of the curvatures are these three, and we translate them into these target space indices by this action of H on this. So this is how we get these three objects. This one, this would be the curvature like Riemann curvature like object, and then we get an additional object. Okay, so yeah, it turns out that so this object is directly the object that we want. It's directly generalized torsion from, so this would be like ordinary double field theory, but here it's a very natural definition. So we just had to have this twisted Dorfman bracket, and then this generalized torsion just comes out as this component. It turns out that this is not as clear for this object. So for this object, can decompose into two parts. So one will be symmetric in the exchange of the first two and last two indices, and so this will be symmetric. Okay, and by the way, here it should be no equals. So here, what comes out is the torsion with this object. So we look at it, we have the ordinary curvature of connection gamma. We have this combination of gammas, and we have this additional field rho, which arises additionally in this Cartan geometry picture. But now if we look at the symmetric and skew-symmetric part, so symmetric part looks like that, and it turns out that this is indeed the ordinary generalized Riemann. So these are the parts from ordinary double field theory. But then it turns out that you have this skew-symmetric part is something which looks like that. So this is just the skew-symmetric combination of these R's, and in addition to this rho. And so this explains, so yeah, okay, one thing I haven't said, that I've got to say, is that with this definition, this object, so I mean, this was the whole aim, to define a curvature object. This is definitely by construction a generalized tensor. So this was the aim, and so all the components are basically by constructions generalized tensors. So also this component is a generalized tensor, and this is weird because it was kind of clear from other works that from just this naive curvature you can't construct tensors, but now we have this auxiliary field rho, this additional object, and basically the way that these objects are not a tensor is compensated by this field. Okay, so this is this object, and so this explains a bit what this is, but I haven't, so we have basically things to explain. So this R we understand, this torsion we understand, and it's very nice that they drop out of this formalism automatically, but at a cost that these objects drop out automatically, we still have to understand what this object is, what this object is, and also, yeah, kind of understand what to do with this additional part of the connection. So it's here and here. So this I want to explain very briefly, maybe one side comment before. So yeah, there is kind of Bianchi identities. So this one is basically known before. So we have basically that this is basically the algebraic Bianchi identity of the ordinary Riemann tensor holds as well in this generalized form. This was known. But we also have some kind of differential Bianchi identity. And in some sense, this is the interpretation of this new, bigger tensor. It is basically just the tensor that tells so this is, here we have this 5-index curvature term, and basically this just tells one what this biagent is, and you can write out this in terms of object like that, and an object like that. So this would be the differential Bianchi identities for R, and this is measured. So I mean, typically in this literature on double field theory and curvature, they say there's no differential Bianchi identity in the sense that this is not zero. But so here we see that these additional objects that we introduce are kind of the objects that measure this term. And so this is object. So this combination is the new object that I will name like that in the following. So just to be clear. So let's very briefly discuss what the meaning of this rho and A is. So this is, you can see quite quickly, in particular in this case, that H is the double Lorentz group. So I've introduced at the beginning these overbart and underbart components. So in general, such an object, so it will decompose into the following independent reactions of these over and underbart indices. And yeah, so these are the only independent components. But now if we look at the definition of this object, this is A in terms of this object. So if this is a curvature and this A, we could interpret the parts of A could be some kind of portion for rho. This means we can use to fix some components of A to be zero. So in particular, we can just, because A is just proportional to rho, we can just fix these objects to be zero. So this, in this sense, is rho is an auxiliary field. We introduce it to just have to compensate the fact that some things do not transform as a tensor. But for H having this form, we can use it to fix parts of this additional A also to be zero. But it turns out this is not, you can't fix all of A. So this is what to do with the remainder of A. And it turns out the remainder of A is fixed anyway by other properties. So this projection is zero anyway. And for example, other of these components will be just proportional to the generalized curvature by itself. So basically the bottom line, if H is of this form, so after fixing rho in a certain way, A does not contain new geometric information. Okay, and as last, so you can do something similar. So for here, now we have to assume that gamma is metric compatible with eta and H, and also with the dilaton. So if you assume this, you can derive basically that also this new, so this, just a reminder, this was this combination of objects. So basically it tells you what is the new objects of this 5-index part of the curvature. And if you compute this explicitly, you see that basically all of the components correspond to covariant derivatives of the Riemann curvature. So these are also not new geometric invariants. They are just they are just combinations or derivatives of the old ones. And it just will turn out that there is components like that are not where it's not possible to write in terms of covariant derivatives of the Riemann tensor, but they contain these undetermined components of the connection automatically. So just as a side comment. So in this sense, so we have analyzed all these additional components of this Cartan curvature and seen that, okay, some components correspond to the ones that we wanted to drop out, come out, the torsion and the Riemann tensor. And so we have seen that we can fix parts of this A by just fixing rho to a certain value, and that then the other components of A and this 5 index thing almost all correspond to just the Riemann tensor or covariant derivatives. So in this sense, this Cartan geometry does not produce like new invariants that we didn't want to have, because we kind of knew that there probably are no other invariants. Otherwise, people would have come up with those. Okay, and I guess time is up, so let me give some very brief outlook. So what we can do from here, so this was just for ordinary double field theory. One can define the same things because it was just relying on these Puron algebroid-like structures. One can do the same probably for heterotic double field theory and for exceptional field theory. And then probably one should, one can, so far we haven't attacked to the problem of these undetermined components. So maybe if one extends this to have this gauge algebra as Maxwell infinity, this will help there. And then also now we have this. So on the string side, there's the story of that this generalized geometry corresponds to generalizations of dualities, and now we have this much bigger space, this generalized tangent bundle of this principal bundle P. And so if we do some kind of rotations there, this should correspond to some dualities. So it's probably also interesting to look at those. So with that, thank you for your attention.
Thank you very much for your cool talk. Very inspirative, I guess. So let me open space for questions, either from online audience or offline audience. So is there any question? I would have maybe a couple of questions. Firstly, kind of provocative question. Maybe I missed something, but how does the current algebra comes in the game?
Sorry, I lost my things there. The current algebra. So yeah, I lost this. The story because I took too long. Sorry. I mean, the current algebra comes in with so if you start with the ordinary current algebra as a string, so that's because the basic motivation. So it was basically the way how Polacek and Siegel constructed this kind of geometry. Is you have this kind of basis of the phase space, and you introduce these additional generators, which again act somehow on this thing. And then it turns out if you compute a Jacobi identity of these things, in particular, I think it's the one where you have S, P, and P Jacobi identity. So this is not satisfied.
Okay.
And what is PM?
PM is so this would be P sigma and D n of sigma. So this would be spatial. So this is on the string. So this would be spatial derivative. And this would be canonical momentum. And so this is the canonical Poisson brackets.
I see. Okay.
Yeah.
I see.
Yeah. Yeah. Thank you for the question. Yeah. So you compute that and you see that basically this object, these generators are not enough. So you have to add an additional object. So basically dual generators.
Okay.
And this is how you end up basically with this bigger space. So you get basically this T plus T star of P out, or this D, and not just, so this object alone is not enough, but you need these dual generators. And this is why because just from the target space perspective, it's not quite clear why you need it, because then there's no problem. But because of this, basically because of this delta prime here, you get some problems. You need to have this additional generators.
And is this generator somehow fixed, or how this is imposed?
On the string. So I mean, this is the kind of dynamical field, and then it turns out this is, so these are the real dynamical fields. This would be the generator, and this was a question what it is, but it turns out you can write down the string equations of motion. So this is basically what I wanted to tell you on this covariant string dynamics part, is that so basically you will have just in a schematical form look like that, and then you will have something like like that. So this would how the string equations of motion look like, where this is a covariant derivative with respect, so with H, where A is a gauge field related to this H gauge symmetry. And here it turns out that so this H as a gauge field arises indeed that the sigma field is one component of these two. So it arises as here, and then you have another component. So this would be A0 and A1 as one forms on the worldsheet. And this, and this would be Lagrange multipliers in the Hamiltonian regarding this SA as a symmetry. So so this SA would be constraints again, and this would be Lagrange multipliers you add to the Hamiltonian. So this is how this sigma arises in the dynamics. But you can also just understand them as like an extension to make this Lie algebra from something which is not a Lie algebra. So I guess it's two perspectives on it.
Okay, thank you. So from the perspective of phase spaces, when you consider strings, should I expect something like you described for the case of particle physics, that there exists some Poisson relation proportional to your curvature?
Yes. So I mean, this is how Polaczek and Siegel came up with, for a certain case, exactly this. So it will look exactly same. So if we have now big currents on the phase space, and now we make a redefinition in terms of so this is the generalized, or our definition of generalized Cartan connection. You look at this, and then you look at the sum brackets of this thing. Now you will get an additional term from this thing, but then as an other term, you will get this Cartan connection as constants. Yeah, it will be exactly. So I mean, this was. I guess this was the original starting point, and the rest we did was just understanding it a bit more geometrical.
Yeah, it looks cool. Okay. So any other question? Not so many people main here. So maybe my last question. I had an impression that once you generalize this, meaning your notion of curvature, you would need to impose term with the RAM differential very naively. Why haven't you chosen this curvature definition with the RAM differential?
Yeah, I mean, yeah, I mean, so yeah, in the end, so I mean, here it's explicitly, so it's written out, and the point is these indices are not. So I mean, if it would be like I mean, I know that probably you and others have thought about how the Cartan differential would look on a bigger manifold, but I wouldn't want that these indices are not constrained by the section condition. So these are not just none of these two. So in this object, none of these is constrained by the section condition. And yeah, it was just a quicker way. You can, I guess, also just find some way to write it in terms of Cartan differential, but actually because it came from this. So what we've written here is always some kind of Goffman bracket. So it was just from this perspective very natural to write it in terms of this Goffman bracket. Yeah. But yeah, I would be very interested if you find a nice expression in terms of Cartan differential on this on an extended space or something like that.
Me also.
Maybe a small remark. So this JA you introduce, in part it has this P with normal M inside. And I think this is the currents I consider Anton, Alexeyev.
Yeah. Yes.
Actually, your S's, they have commutations relations, Poisson brackets with P's, which seem to be that the S's also can be at most linear.
Yes.
So in P's. So maybe they are the same form. So maybe the whole thing is just like again of our current algebra, just a sub-algebra of this, where some of the currents generate some group action. Like if you look, for example, you can generate Kac-Moody, right? And I mean, your brackets, if you have down there, they are precisely of this of the form we had, right? Some delta term, some delta prime term, and there's some hidden the current bracket inside, but you can retrieve cases like the Westermino-Witten double model, and if you look at particular currents.
Yeah, I mean, we also, I mean, I think we thought about it a bit differently. We thought about that this big thing would be just a representation of this, of your thing, and then what we basically do, because this basically is, or this is also related to this other paper we begin with Algebra, is basically that we do kind of reduction of this thing, because we say that some of these generators are 0. But yeah, I mean, you are right that if we, I mean, you're most definitely right that if we assume this relation, that this is probably very restrictive, and it probably is.
Again, of the, so it's just like a bigger current, which is again of that form. We just have
of course. I mean,
this line, I think.
Okay. Yeah, I mean, we didn't intend to state something different, and maybe just one side comment because it's related. I guess you. So I mean, this is very natural because this would correspond to like a reductive action of this H on the generalized tangent bundle, but I think you can, it might be that you also have to consider for certain cases that you have terms like that. Nothing would go wrong. So I mean, this is just the easiest way, and actually the way I wrote it here. So there's no restriction on the action of H on D. So all of these definitions, they go through. You can define some covariant curvature if this is not zero. This was just the easiest example, but I think in general you can have terms like that. It's just it's not as intuitive.
Okay, any other question? It's not the case, so let me thank the speaker again.
Yeah, very nice, David.
Yeah.
Okay.
So they're happy you came, and you can look forward to the next week. I don't really know who's gonna have a talk. You'll get to know soon. So.
Yeah, but I mean, what you when I may say what you were saying about this kind of writing it in terms of a differential is really interesting. So we also thought a little bit about it, and it's a little bit hard because I mean it's geometry, right? So I mean you would have, I mean you have to deal with this kind of Courant algebroid, and so in a way there is no really difference between vectors and differential forms, right? Because a generalized vector has both, so it has a vector component and it has a form component. So and I think there are some approaches to write down, for example, the Dorfman bracket in terms of differential operators, but it's for us not completely clear how one would write this kind of thing in this form. Okay. So it's a good point. I mean, the equations we found, they are working, you know, and you have a nice definition, and you recover your curvatures and everything. So what you also would get in normal Cartan geometry, and you can mimic all the properties of the Cartan connection, which you would expect. But I agree, it would be very nice to be able to write it really on the same footing and see that these equations look exactly the same.
If I got it correctly, your first motivation, or one amongst others, was to come up with some reasonable notion of connection, as to have this property of being a tensor under a generalized diffeomorphism.
Yes.
And this might go along with this additional term as well, I guess.
Yes. So this exactly. So this is one motivation. Another motivation, which I think is nice in the context of string theory, is that, you know, the motivation behind Cartan geometry is usually that you want to think about homogeneous spaces, and that you want to go away from homogeneous spaces. And so when you have something which is very close to the homogeneous space, then Cartan geometry works best, because you just describe the homogeneous space. I mean, on the tangent bundle, right? But this is a way you can do this very nicely. And when you think about homogeneous spaces in generalized geometry, so you come naturally to the notion of dualities in string theory, and you actually find that all the different dualities you find, so they can be just realized at homogeneous spaces in generalized geometry.
Okay.
So, which is actually a quite powerful thing, because of these different dualities, they can look very, very different. So, but you know, they are unified in this nice way as actually a homogeneous space. And this is something I was always wondering, perhaps you know more, but I've never seen mathematicians really discuss homogeneous spaces in generalized geometry. I mean, in principle, you would think this is the most natural thing they would do. But there's actually not much about it what I found or could at least understand.
there is some material recorded in 2016, I guess, when Schreiber had the series of talks about super Cartan geometry and generalized geometry combined. But the quality of the recording is not very nice, so I can send you this. Like the recording, but it's hard to
get, right?
It's
hard to get, and maybe I even don't understand their mathematical language, because it might be very advanced. No, but you see, from a physics point of view, it's very neat, because so these kind of spaces, homogeneous spaces, which you can define in generalized geometry very similarly to you would do it in normal geometry. So they have some additional properties, which actually is exactly what you need to have these different dualities in string theory. And so we thought we want to have a geometry which is more also adapted to this idea of dualities, which I think is some of the origin of generalized geometry. And when you do this, you get all this nice structure that David was explaining. So that was another motivation of doing it like this. Okay.
So I should stop recording, by the way. I forgot this.
Oh, okay. So now we can also say inappropriate things.